Hi everyone, my name is Patrick. I work at the Met Office in Exeter in Devon, and I'm here to talk about Biggus, which is our approach to just handling very large data sets, really, bigger than you can easily manage in your machine memory. I should say that we have about 400 scientists working in climate and forecasting research, and there's a small group of us, around about 8 people, just doing support and development for scientific data analysis and visualization software. And this is just a small part of that. Our big project is really IRIS, which is an analysis and visualization library, which I shall touch on very briefly later, how this plugs into that. Okay, so this was actually the title of my talk. Biggus is a lightweight, pure Python package, etc., which implements lazy operations on NumPy array-like objects. What does this mean? Okay, well, it aims to just make data analysis on large data sets easier, like it says there. It avoids scalability problems, which is basically we have people who come to us with a solution in terms of a chunk of code that does some analysis on lumps of data, and then the next generation of the forecasting model comes along and the data's got 8 times as big, and that operation no longer works because it simply can't cope with the amount of data. It also, by kind of separation of concerns, makes the code much clearer and simpler. I'll explain that a bit clearer later on. And also, it's actually more efficient in terms of space and time. And the key technique by which this is all achieved is this thing called lazy evaluation, which, as a short strapline, don't do it until you have to. And this will be common to many of you from languages that embody lazy evaluation, like Haskell. But we have a much more simpler way of approaching that, which is entirely explicit in its usage. It goes by several basically interchangeable terms that you may have heard. So you have virtual arrays, or you have lazy evaluation, or you have deferred evaluation. And those 3 things, I apologize if I use them interchangeably because they are virtually interchangeable terms. So Biggus itself provides virtual arrays within Python. And the key point is that a virtual array doesn't need to know the actual content of the data. What it does know is the size and shape, in terms of NumPy, literally the shape, and the data type, in terms of NumPy, literally the D type. And on request, it knows how to get at any kind of slice of that, any section that you would make using normal NumPy indexing. And we can process these in various ways, and such processing, for instance, combining things, extracting things, doing arithmetic, doing statistics, they produce new arrays, just as they do in NumPy, but the manipulations don't process the actual data. What you get is a resultant Biggus array, which can provide you with the data result, but is kind of not expecting that you need to actually do all of that until it's asked. And oddly enough, that gets you all the benefits that I previously discussed. So you can have arbitrary data size, you can have optimized data access, and you've separated your data analysis handling from your actual analysis code, because you no longer have to rewrite your code because it can't handle the amount of data that you're now throwing at it, whereas it previously worked on a small test case. So the features that it provides, basically the arrays themselves, you can combine them and extract from them using indexing. We can do statistics and arithmetic, and it has a thing that you don't much see, which actually effectively implements all those things. And the way I'm going to just run the rest of the talk, I'll start with a very simple example. I'll just go a bit more into what it's good for. I'll give a summary of the actual features, and just to very briefly touch on how it works, and then kind of wrap up, sort of say things about the future and see how it wraps up. So the easiest way of running it, this better work. There you go. As you can see, this is still alpha. It's still quite a new product. we've only had it now for, I think, not even 2 years yet. So in NumPy, a mean calculation looks like this. I'll just run this. Nothing to be surprised about here. So you create an array, you say dot mean axis equals 1, you get these values as you'd expect. So the point of this is to show the equivalent in Biggus. Unfortunately, I couldn't fit it on the same page, but never mind. So that looks like this, or at least this part of it looks like it. So what I've done here is I've created a lazy version of that array, that same array I just created. That's a lazy version of it. I'm just printing that out. Now this, of course, doesn't have the data, but it knows what it looks like, exactly as I just said a while ago. And if I now just kind of repeat that, this is actually using it. So I've taken a mean of it. It's a similar kind of thing. Biggus.mean could just as easily be np.mean. Across the axis 1, you get a result, which I'm calling lazy mean. You see that here, it's printed out. It's still not actual results. To get the results, this is the key point, this thing here. I guess I could do it like this, couldn't I? That is the key, that's the key operation that's provided to actually get results. And of course, the goal, the game, if you like, is not to do that until you have to, or at all if you don't have to. So I'll just make that point by redoing it, and I'll just run this. So what we've done here, that's exactly the same extraction as I did before. I've just created another one, same thing, printed it out. But this time I've altered the underlying array, and now when I calculate the mean, the results changed because it didn't actually do the calculation at this point. It does it here. Simple as that. So, what's the point of all of that? I've already touched on this briefly. Biggest issue is that in order particularly to do statistics, you don't have to load the whole lot to get the result. It can kind of process things that are larger than the available memory. It knows how to divide up the task and present you with the result. Secondly, you can actually make that faster, particularly when you have to do multiple calculations on the same data. So obvious ways of doing this would involve loading something and then creating 3 statistics, and each one would take some time. And if the data is larger than you can actually store, that creates its own problems. But by deferring the operation and representing it as a kind of a specification of what's to be done, rather than doing each thing in step as you write the code, you can do that quicker. And the code thing is that basically you do all that without having to think about the deferred operation part of it. So the code you write looks very much like NumPy code because you're still doing the iterative processes in the order in which you think of them and in the way in which you think of them. In terms of the space, here's our problem. This is our own, the UK Met Office global model. This is the resolution, the history of it over the past, whatever this is, 20 years or so. So that's the X and Y resolution. And this is the Z resolution, which has gone up from 20 levels in 1990 up to 70 levels today. And the total number of points per data frame has now gone up from about 1 million to about 55 million. So a single forecast data field now occupies a couple hundred megabytes, and there are hundreds of those in a run output. A standard dump file is now something like 4 gigs. And we do a new one of those every 6 hours, and some people want to kind of load in a week's worth and do something with it. And of course, this was, in these days, that was manageable. But now it's getting increasingly difficult. So the key point with time is, I shall be discussing this later, I'm not going to, is basically just, as I said, to avoid rereading anything, especially if it's coming off disk, obviously, as it usually will be, and to do your calculations in parallel. And that also gives you a hook, which we do not yet have, but to future actual concurrency and distributed processing, i.e. taking the operations to the data. so the thing about the code, the easy way to write an analysis process, when you're prototyping something, you take some arrays that have got the data, you write your code that does some calculation, and you don't worry about the rest. Code written with Biggus, as you will see, looks very similar, but deferred execution means this has complete scalability, and you don't confuse that with the access code. And I'm just going to say a little bit here about the... this again this is in Iris. This is not really a plug. This is our main product, which is a thing in which you can load various sorts of geolocated data and other stuff. And we have a common way of viewing data that comes from different sources supplied in different file formats, and we try and manage all the metadata the best way we can. So this is something that's loaded, and this represents all the associated information. It's only a 2D field. It's a very small one in this case. But when we were writing Iris, at one point we had we want to be able to load a really big file and have what appears here as a kind of a catalogue of it. So already from way back we had this concept that we weren't loading the data at this point. The key data that forms what you see here wasn't in this listing. It's only got like a pointer to the file or something. And we had a way of doing that. And then we added another file format, and we had a slightly different way of doing that. And then these things are actually objects which you can sub-index and extract bits of. And so we end up having to kind of having to think about how you could do that with two slightly different deferral schemes. And Biggus just, when it came in, just got rid of all this, and the third file format that we just never could get round to implementing, and that was looking like a real problem, it just fell out. And suddenly we have an integrated solution to all three and whatever else you want, and it's much easier. So just for the features index here, these are like the 4 areas in which I'm just going to discuss the features that are coming up. The first one is obvious, really, but the key to this is that everything that you do produces another Biggus array object, note the capital A. So all of these things can be combined freely, and you get the benefit as long as you stay within those operations and don't actually realize anything, don't call the ND array operation. So basically all of them supply at least this the basic ordinary NumPy indexing. So you can extract a column, you can extract a row, you can extract a region, and here's a kind of a sparse indexing with the equivalent of which is here. So it's sort of chopping out these 3 columns but only selected rows. And I'll show you. So to have something that looks like an array, in other words, to write a wrapper so that you can view your data as whatever data source, whatever it is, you really just need to fake up these 3 things. These are the things that we consider you to need. So you need a shape, a data type, and an indexing hook, which is just standard Python. It's just a get item call. And here's an example of that. I'll just run it. What I'm creating is a thing that looks like an array of a given shape full of constants. So I have there, I'll do it this way. I have there the shape and the value which you pass in when you create it. It stores that away and the data type. And when you fetch it, it provides a manufactured array of that size, and it's all equivalent to the value that you've asked for. And the only slight little hook is that there's a print statement in there. So whenever you do it does actually access the data, it prints out to tell you what it's done. So what it's showing you here is that's the array version of one of those. So you wrap it. This is the same wrapper object I used before. It's treating it like a NumPy array. You create a constant array, print that out. It knows what it is. You index it, so you kind of strip away the first 2 indexes and just wind up with something which is 4 long. And there it is. And only when you actually print it, only when you actually do this, get the results, it then prints out that thing to show you it's done it. Just a kind of a tiny proof of concept of how easy it is to write a wrapper. In actual fact, this particular instance simply exists in Biggus. There's a thing called a constant array, and that produces exactly the same results. Right, so now it gets nicer. So there are 2 ways of, and this is There are two ways of taking a bunch of arrays and making a big array out of them. There's two kind of obvious ways. One is to kind of stack them up so that you create an extra dimension. The other is to put them side by side. I'll show you what I mean. So this is array stack. You give it a bunch of things, all of which have to be the same size, and it simply creates a new dimension and stacks them up. So here we have 3 by 4, 5 of them, and you end up with something which is 5 by 3 by 4. That's fairly straightforward. And here's a code example, what it's worth. Just run that. So what do we see? I've created 5 of these. So I've got arrays 1, 1, 1, 2, 2, 2, 3, 3, 3, and so on. I've stacked them together, and you just see a multi-dimensional result. Pretty much what you'd expect. Now, the interesting one. This, I should have said, whereas that is actually equivalent, that is equivalent to stack in NumPy, H stack, V stack, stack column, stack row. This is equivalent to this next thing, which we call a linear mosaic, is a kind of a tiling concept which joins things edge to edge, and it's equivalent to NumPy concatenate in that respect. Now, it doesn't create a new dimension. What it does, that's right, I forgot this. What it does is it pastes things end to end. So these are the same arrays I had before. I had 5 of them, 1, 1, 1, 2, 2, 2, 3, 3, 3, 4, 4. I changed one of them just to show that you can combine things of different sizes here, and it's just kind of stacked them all together. And that no longer knows, essentially, about the division between these different data sources. They could be wrappers around large file objects. It doesn't care. So as far as Biggus is concerned, this is just an array like any other, and that is really important. The fact that it handles irregular sizes and is seamless. Here's an example, just a graphical example of what you could do. So I've got a bunch of things here. It happens that they form a regular array of some sort. They don't even need to do that. The rows could actually have different orientation. I just couldn't be bothered to draw it. But you can extract an arbitrary region, and it's completely seamless and it doesn't care. This is a really hard thing to do. This is very useful for us because we deal with data that's based on calendars. So you have a bunch of files, and each file represents a month, and so of course they're different lengths. But with this means you can patch it all together and just say, I want from that day to that day, and I get a flat array with uniform indexing. And then when you access it, of course, it chops the right bits out of the right files and patches them together without you having to think about it. And that's where it gets hard when you're writing your own code and trying to do this by steam. So I'm just going to move on now to, just quickly, this is kind of the meat of it, really. We have a mean operation, which does pretty much what you'd expect. So there is no mean, not till I ask for it. You've already seen this, in fact. This is the simple example. And we have a set of other small statistics that do a similar thing. We haven't actually implemented much of this. We've implemented only really what we need at this point. So it's very basic statistics, but it kind of shows the principle of being able to distribute the operation. And the effect of that, sorry, I don't mean that. The essence of that is that each of those statistical algorithms needs to be re-implemented in a very standard, obvious way, which is that you initialize something and then you process data in chunks as they come from it, and then you produce a result at the end. So it's like, at this level, that operation has to know about how Biggus works. And the way the data is split up, which is I'll be discussing very briefly later on, is a clever thing called an engine. And the key point is that the statistical operation doesn't actually care about how it's chopped up. It has to handle with what it's thrown. With one exception, which is that, as I've suggested here, some statistical operations need to place constraints on how the data is chopped up. So there would be, for instance, something like a median function, or somebody was talking about histograms earlier on. Those things are rank statistics, so you need all the data because all your categorization might change if you get one more data value. So what we would require, we haven't actually written this yet, but it would need to be able to specify that it needs all the data along the aggregation axis in order to do its calculation at each point. Although we haven't got this, we have got the hook for it, so it's kind of the structure is there to produce things that do that. And then just very briefly, we have simple arithmetic, which is as obvious as you might think. So we can add things together. And we literally, I think, just have add and subtract at the moment. I'm not sure there are any other arithmetic operations. But the key thing about this is the implementation of these. If you want to make one, it's a very small module. It's very easy to add something. This is much more straightforward because it's just element-wise. Because these intrinsically, they are like NumPy ufuncs, so they don't care how the source data has been chopped up. They've just got a little bit of it and a little bit of the same thing else there, and we just combine them point by point. So that's a much easier thing to generalize, and you can just make one of these by passing a function. So, how does all this work? Well, the point of it is to scan large data sets in a kind of a sequence and process it in bits and put it together at the end. And the advantage, the way that we've done this, the way that this works is that you have a kind of a representation of what is to be done at each point rather than having actually, I've taken the mean and now I'm going to subtract 3. So the benefit of that is that abstraction means that it leads towards parallelism. And it also means, in this case, that we can say, oh, but I know how to do that, so I don't have to read the data 4 times. So this is a very simple example of that. This is like it's a demonstration of how that works in terms of a graph, really. So instead of having just a chunk of code, this is the code that would give rise to this. So here I should explain this carefully. I have 2 sources of data called A and B, which may be just large files. I take the mean of one, I subtract that from this, so I get kind of another stream of data, if you like, and then I'm taking 3 separate statistics and storing them somewhere else. All that in Biggus is done by this code here, which looks like the analogous operation in NumPy. So I take a mean, I subtract 2 things. We don't actually have an override operator, but you just have a dot sub, and I can take those and save them here. The key part is this, where it says, actually this might not work. No, it does work. There you go. The key part is that one there. So in order to work this, I'm not calling ND-array on an individual array anymore. I'm saying I need to, in parallel, evaluate these things. That's literally what it means. It says, I want those 3 things, I want you to do it all at once. So that's what it does. And I'll just show you a very brief code example of that. It's probably not delivering a great deal, but just to prove it works. So there that's a piece of code that represents what you've seen before. This just sets up some data, which looks like that. And I want to calculate, basically count the data, take the mean and the standard deviation at the same time. And you do that using this call, and it just delivers as you would expect. So basically, just kind of what I've said really. The existing features, the status of it is, the existing features are immediately useful. We are using them in Iris for deferred loading and for simple statistical operations. And it provides the arrays, combine and extract, arithmetic and statistics, and the sufficient valuation thing. But there's a lot missing, which is mostly just kind of joining the dots, filling in the blanks in many cases, like some statistics that we could have that we just don't at this point. What we would like to add to it, which we already have prototypes for, is saving things direct to file. Some more intelligent strategies for actually deciding how you carve up and how much memory you assign to individual parts of the operation, and just more functions for what it comes down to is whatever gets asked for, because we have a huge pile of things to do, and we work in an entirely agile fashion, which means that we have to prioritize what we do, and it's a question of what we're asked for. So there you go. It's a fully open source project. You can download it and run it, and it would be really nice if you did. Just give it a try, and we need more feedback, and we're looking for it here. Thank you.
So we have time for a couple of questions. If the next speaker in the meanwhile.
Very, very interesting. I was curious about two things. Can Biggus do sub-expression eliminations of like partial quantities? If you're evaluating a relatively long expression, can you avoid creating the temporary arrays? Do you just pipeline everything through?
It won't avoid creating temporary arrays. I think what you're saying is it would potentially create two to evaluate two parts of sub-expression. No, it can't. We don't have a clever reduction. It could do because the structure of the representation is such that you could add such things. But at present, it doesn't do anything very clever at all. It only does what we need it to do, which is fairly straightforward at this point. So basically, no.
Okay, no, that's
It's an interesting idea.
Hey, it's a cool project. It's very useful set of functionality. What's striking is that it overlaps with things like Blaze, from Continuum. And I'm sure, so are you aware of the Blaze?
Oh, yes.
Yeah, and I'm sure you're aware of the overlap. And so, of course, as somebody who would probably like to use this functionality, I'm disappointed that you guys are not working together, and I absolutely can understand why. Two big different organizations.
No, that's not the reason at all. The point is that when we came to make this decision, when it was important to have something, we didn't feel that Blaze was mature enough, and we needed something we could control, however simplistic it was to start with. And that's really why we've gone down that route. It wouldn't be hard to change. We've already changed once in terms of how we represent these deferred operations. So, like as regards within Iris, which is all that our users get to see of this at present, that's not a problem. We could change that.
Okay, that's interesting. Thank you.
This is the last question.
Thanks. And for instance, if you wanted to compute the maximum along the time axis or the minimum, is it implemented already, or do you have to recode it?
No, it's not. There's many things which would clearly be trivial given what we've done, but it's just not there. Min and max are in some senses even easier than sum and difference, but they just aren't there at the moment. You could add it in an afternoon. It's as simple as... Oh, they are there now, are they? Yeah, sorry, I checked on that only the other day and discovered they weren't. That's how it is. Very agile, you see.
Okay, thank you again.
Thank you.